Sorry for the delay here. Thought I had it set up. So we're going to be going through Chem 102, Chapter 15, the first sections in this video. We're going to be covering sections 15.1 and 15.2 here. So first, we're going to talk about what is spontaneous. So a spontaneous process is one that does occur in that set of conditions. And so if you see a chemical reaction and it is happening, that is the spontaneous process. A process that does not occur under a specific set of conditions is called non-spontaneous. Non-spontaneous processes do not occur unless they're constantly putting energy into it. Like you can have a non-spontaneous process, but this one needs constant energy input. And I have an example for you that will help. So there's some examples of spontaneous and non-spontaneous processes. So for example, ice melts at room temperature. You set ice out at room temperature, it's gonna melt. Is it gonna freeze at room temperature? No, that's non-spontaneous. Sodium metal reacts with water to produce sodium hydroxide and hydrogen gas. That if you just put sodium metal in water, it's going to be violently reactive. If you're not sure, if you don't believe me, just Google sodium in a lake. There's a bunch of country folks. It looks like country folks that go out and just take a big brick of sodium. I don't know how they got this, and they just dump it into a lake, and it's a big explosion. Sodium hydroxide reacting with hydrogen gas. So reversing this reaction to make the sodium hydroxide and hydrogen gas the reactants producing sodium metal and water, that would be non-spontaneous because we don't see that just happen. A ball rolling downhill would be spontaneous. A ball rolling uphill would be non-spontaneous. How do you get a ball to go uphill? You would have to constantly apply energy to get that to happen, right? So that's non-spontaneous. Iron rusts at room temperature, but is rust going to turn back into metal at room temperature? No. And water freezes at negative 10 degrees C. True. But would ice melt at negative 10 degrees C? No. The melting point of water is 0, and negative 10 is less than that. So the process that results in a decrease of energy of the system is often spontaneous. And so a lot of times our exothermic processes are spontaneous because they give off energy. So combustion reactions, this is a combustion reaction. Combustion reactions are always spontaneous. So we don't have to say spontaneous combustion. Combustion is always spontaneous. And we'll talk about how we know if something is always spontaneous or spontaneous only in certain conditions a little bit later. However, the sign of delta H alone is insufficient to predict spontaneity in every circumstance, right? So in the combustion example, it's exothermic and it's always spontaneous, but it's not always spontaneous because it's exothermic, because here is an exothermic process, liquid turning into solid. That's exothermic. That is freezing. But it doesn't happen. It's not always spontaneous. This is only spontaneous at lower temperatures. So liquid doesn't turn into solid at any temperature, only at low temperatures, so below 0 degrees C. I think it should be temperature is below 0 degrees C here. Temperature is less than 0. So when the temperature is less than 0 degrees C, this process will be spontaneous, and it's exothermic, right? So it's not that every exothermic is always spontaneous. So we have to get that kind of out of our heads because that doesn't help us here. And this process only happens when the temperature is low. We only have liquid go to solid or freezing when it's lower temperatures. So there's another factor that must be making the decisions about spontaneity, because there are these like certain temperature factors And then there's some stuff that's like spontaneous only at high temperatures, like melting. What about endothermic stuff? We've talked about endothermic stuff before. What do you mean to tell me that every endothermic reaction is just non-spontaneous? Well, that's not necessarily true. So there must be another factor. The other factor is called entropy. Entropy, which is given as the variable S, is a measure of how spread out or dispersed a system's energy is. And we can also think about it. We can also think about the particles because for us, we can't really see energy. So it's kind of hard to think about that. But if you think about particles spreading out, then you are kind of spreading out the ability for those particles to hold energy, to spread out the energy. So if we have a box like this would be lower entropy, and now we release it, and now there's more ways in which we can arrange the particles. And so when we're thinking about entropy, we can also think about entropy is a measure of all the different ways energy, and then we can also think about it in terms of particles, can be arranged. So you can imagine if you're in a smaller container, the arrangement of particles is more limited. If we open up to a bigger container, the arrangement of particles there's more different ways in which we could arrange them. So we would have a higher entropy in the second scenario. So changing the volume available for a gas to float around in can increase or decrease the entropy. So spontaneity is favored by an increase in entropy. So, well, let's go back up here. I want to say real quick here. Spontaneity is favored in exothermic processes. That doesn't mean that endothermic processes can't be spontaneous. You know that some endothermic processes, like melting, are spontaneous in certain conditions. But what's favored are exothermic processes. So exothermic is always going to be a little bit easier to get something to happen. And then if you have something that's exothermic and also has an increase in entropy, that's really good for spontaneity. So we say that's thermodynamically favored to have exothermic and increase in entropy. Entropy can be given by this formula. So S is our entropy. By K, which is called the Boltzmann constant, ln W. And W is the number of different arrangements. Sometimes we call these microstates. Each arrangement is called a microstate. So like imagine that you take a picture of each arrangement. That's one microstate. So W is just counting how many of those. The number of arrangements or microstates possible is given by W is equal to X raised to the N, where X is the number of cells in a space and N is the number of molecules. And we'll talk a little bit more about these. You don't really need to worry about doing math with that guy. So what I mean by how many cells in a volume, like how many, so this would be 2 cells versus 1 cell in a space. And then N is the number of molecules. Never mind. That's opposite here. So let me come back to you with this, but we'll talk about it. Yeah, so here we are talking about it. So 2 molecules and 2 cells. So there's imagine if we took this and we were to separate it into 4 different areas. I'm going to show you there's a website that I'm going to show you in class that actually explains this a lot better. So let me get into that in class. But so there's 2 different molecules and 2 cells. And so there are possible arrangements if we have thinking about 2 different ways. We can have both the green and the red on this side. We can separate them. We can separate them like this. We're having both on that side. So there's two cells. The cell being this one and this one. If we open it up and now we have 4 different areas there can be. So you could have separated, same side, separated. And so there are these different arrangements. Again, I'm going to show you a website that's going to walk you through. I think it's a little bit easier to understand the different cells, I guess. The most probable state that it's going to be in is the one that has the most arrangements to be in. So change in entropy is what we're going to talk about next video. So we'll just stop here and then I'll go through this whole cell stuff with you in class. It'll make a little more sense when I show you the website in class.